Imagine looking up at the night sky and thinking every little fuzzy patch of light is a neat, self-contained island of stars, like our Milky Way, tidy and glowing. The universe is not that tidy. Galaxies come in strangest shapes, sizes, and moods. Some hide almost entirely from view, barely whispering their presence to our telescopes. Others wear perfect rings, as if someone sculpted them with a cosmic cookie cutter. And then there are objects that look like someone rearranged the rules of how galaxies are supposed to behave. They're the culprits behind the coolest mysteries astronomers are trying to crack right now. Dark galaxies, ring galaxies, and a whole zoo of bizarre cosmic structures. Let's start with dark galaxies, a phrase that sounds like science fiction but refers to a serious and simple idea. A dark galaxy is a region of space where there seems to be mass, sometimes a lot of it, but almost no stars. Imagine a town with the infrastructure of roads and buildings, but no people living in it. You can see the street grid from above, but no lights are on. In cosmology, the streets and buildings are the dark matter halo and perhaps clouds of gas. The lights are the stars. For decades, computer simulations of the universe have predicted many more small clumps of dark matter than the number of dwarf galaxies we can see. This mismatch led to a question. Are there a lot of dark matter halos that never grew stars, literally dark galaxies? Or are our models missing something important about how galaxies form? Detecting something that is, by definition, dark is tricky. Astronomers rely on indirect clues. One of the most powerful tools is the radio wavelength, where neutral hydrogen, the most common gas in the universe, emits a faint signal at a specific frequency, the 21-centimeter line. A radio telescope can sweep the sky and find clouds of hydrogen gas by their radio glow, even when there's hardly any starlight. Over the years, surveys that map this hydrogen have turned up objects that looked like gas clumps with no visible stellar counterpart. Some of these were strong candidates for dark galaxies. If you find a big, rotating blob of hydrogen but no stars, it almost screams mystery. One famous candidate was an object that goes by the short name Virgo 21, spotted in the early 2000s in the Virgo cluster region. It showed up as a neutral hydrogen detection, with signs that the gas was moving in a way consistent with a massive, rotating object, as if there were a dark halo twisting the gas around. For a while it made headlines as a potential dark galaxy, because deep optical images didn't reveal a matching galaxy. Exciting stuff, but science is rarely clean-cut. Later, more detailed observations suggested a different story. The hydrogen turned out to be part of an enormous stream of gas pulled out of a nearby galaxy during a dramatic gravitational interaction. In other words, Virgo 21 might not be a ghost galaxy at all, but tidal debris, a swirl of gas flung into space during a galactic tussle. That taught a useful lesson. Nature builds convincing lookalikes, and you need multiple lines of evidence to confirm something truly lacks stars. Similar tales popped up elsewhere. Large radio surveys like Alfalfa, the Arecibo Legacy Fast ALFA survey, found many faint hydrogen sources, some of which had very faint or no optical counterparts. These objects prompted careful follow-up work, often with deeper optical imaging, or by looking at the environment around the gas. Astronomers found a galaxy nearby that had recently been stripped of its gas by gravitational interactions, or by the hot environment of a galaxy cluster. So some suspected dark galaxies turned out to be ghosts, left by violent encounters. Gas that's been ripped free, but not necessarily a gravitationally bound dark matter halo with no stars. At the same time, a separate but related class of objects nudged the dark galaxy discussion in a different direction: ultra-diffuse galaxies, UDGS. These are swampy, faint galaxies that can be as large as the Milky Way in diameter, but contain maybe a few thousand to a few hundred million stars, tiny compared with the hundreds of billions in a typical big spiral. They're so diffuse that they're easy to miss against the background. UDGs like Dragonfly 44, discovered in the Coma cluster by a team using a special Dragonfly telephoto array designed to detect low surface brightness objects. appeared at first to contain surprisingly little starlight for their size, while behaving gravitationally like massive systems. In one early study, Dragonfly 44's motion of star clusters suggested a lot of unseen mass, implying it might be overwhelmingly dark matter dominated. Practically a failed Milky Way that never formed many stars. Later reevaluations of the data reduced the implied mass, but the object remains a striking, fluffy galaxy that challenges how we think stars are born and retained in dense cluster environments. Then came a different shock. In 2018, a team reported two faint galaxies near the Big Elliptical Galaxy, NGC 1052, named NG Cone 1000 and 52D F2O and DF4, that seemed to have far less dark matter than expected. The usual story is that stars sit embedded in a large dark matter halo. Here, measurements of the motions of star clusters around DF2O suggested almost no dark matter at all. If true, that would be revolutionary. But astronomers are cautious, and later work showed the result hinged on the galaxy's distances. How far away they are affects how big and massive they appear. Changing the assumed distance can make the dark matter deficit vanish. The episode is a good example of how messy real data can be, and how extraordinary claims require extraordinary cross-checks. Still, DF2O and DF4 forced the community to think creatively about how galaxies might form with unusual dark matter-to-stellar ratios, whether because of violent interactions, stripped halos, or quirks of their birth environment. All of this hydrogen clouds with no stars, ultra-diffuse galaxies that are big but faint, galaxies argued to lack dark matter, feeds into a larger question. How does environment and cosmic history influence whether dark matter halos become bright, starry galaxies or remain dark, or somewhere in between? There are several plausible reasons a halo could stay dark. First, it's about gas cooling and compressing enough to ignite star formation in the first place. Small halos might not pull in and hold onto gas efficiently. In the early universe, the background of ultraviolet radiation from the first stars and quasars reionized the universe and heated the intergalactic gas. Tiny halos might have been unable to accrete cold gas in that hot soup. In clusters, the hot intracluster gas and interactions with other galaxies can strip gas from a small object, leaving it gas-poor and unable to form new stars. Or the gas might be present, but so diffuse that it never reaches the densities needed to form stars. So dark can be a temporary state or a long-lasting fate, depending on circumstances. Upcoming radio observatories like the Square Kilometre Array SKA and surveys with current instruments, MEERKAT, ASKAP, should give us far deeper and wider hydrogen maps of the nearby universe. If there really are many isolated dark halos filled with gas, these instruments will find them. If not, we'll learn more about how interactions and stripping carve up galaxies. Either result tightens the screws on our models of galaxy formation. Moving from things that hide themselves to things that show off their shape, ring galaxies are another class of visual oddities that astronomers love because they tell a clear story about cause and effect in the cosmos. The archetypal ring galaxy looks exactly like it sounds. A bright, often blue ring of stars surrounding a central core that is less active and looks older. One of the most famous is the Cartwheel Galaxy, whose luminous outer ring is studded with bright blue knots, star-forming regions packed with young, massive stars. The intuitive explanation for many of these glorious rings is a head-on collision. Picture a calm pond. Drop a stone near the center and waves ripple outward in concentric circles. If you could do the same with a flat disk galaxy, send a smaller galaxy plunging straight through the middle of it, the gravitational disturbance acts like that stone. Stars don't bump into one another. Galaxies are so sparse that direct collisions between stars are vanishingly rare. But gravity reshapes the orbits of the stars and the gas, generating a ripple that moves outward. As the ripple sweeps through, it compresses gas, and compressed gas lights up with bursts of star formation. The result, a ring of newly minted stars expanding outward from the center. The ring can be remarkably symmetric if the impact is fairly central and along the disk plane, though off-center or angled collisions make more messy rings, arcs, and spokes. Not every ring is a collision score. Some rings are born internally through resonances in barred galaxies. Imagine a galaxy with a central bar, a long, flattened structure of stars crossing the middle of many spirals. The gravitational tug from that bar can drive gas into resonance zones where it piles up and forms a ring. These rings tend to be smaller and centered on features of the bar pattern, rather than being large, explosively star-forming collars like the cartwheel. So when you see a ring, astronomers ask whether it's a collision-driven ripple, a resonance ring from a bar, or something else. Some ring systems are extreme in their perfection. Hoag's object is a striking example. A nearly perfect ring of hot young stars encircles a round, red central core. Its geometry looks almost like two objects pasted together. How did it form? Theories include a past head-on collision, the result of bar-driven resonance that later dissolved, or the aftermath of a more subtle interaction that left the center untouched. Hoag's object is rare, and because it's so symmetric, it keeps people guessing. Auriga's wheel is a fainter, more recent example where a ring and a companion galaxy are caught in the act, giving good evidence for collisional formation. There's another beautiful twist. Rings can be formed by gravitational lensing. If a massive object, a galaxy or a cluster, sits almost exactly along the line of sight between us and a more distant galaxy, the foreground mass bends the light from the background galaxy into arcs or even a full ring, a phenomenon called an Einstein ring. This type of ring is not an object in its own right, but an optical illusion made by spacetime curvature. Einstein rings are powerful tools because they give a way to directly measure the mass of the lensing object, including its dark matter, from the ring's geometry. Back in the realm of physical collisional rings, there's also a close relative called the polar ring galaxy. In those, a ring of gas and stars orbits almost perpendicular to the plane of the central galaxy. It's as if a flat galaxy has a wide bracelet tilted at right angles. Polar rings are fascinating because they provide a three-dimensional probe of a galaxy's gravitational field. A well-known example is NGC 4650A. These rings almost certainly came from accreting material. Perhaps a small gas-rich galaxy that was captured and torn apart in an orbit that deposited material into a polar configuration. The polar ring then rotates in a plane different from the main galaxy, letting astronomers map the underlying mass in more dimensions. Rings give us snapshots of destructive or creative events. They are snapshots in time where gravity's choreography is temporarily legible. In some cases, the rings fade and the galaxy blends back to obscurity. In others, the ring might collapse, form new stars, or seed a new disk. They're a reminder that galaxies are not static wallpapers but objects with histories, sometimes violent, sometimes slow and steady. If dark galaxies and rings make you think the universe is both stealthy and showy, wait until you meet the stranger specimens. Objects that don't fit neat categories and force astronomers to invent new explanations. A collection of these are the odd radio circles, jellyfish galaxies, Hani's Vorwerp, tidal streams and shells, and the ephemeral green peas, each offering its own puzzle. One of the newest additions to the catalog of oddities is the Odd Radio Circle, or ORC. These were discovered only in the last few years by surveys using new-generation radio telescopes like ASKAP in Australia. When astronomers mapped the sky at radio wavelengths, a handful of objects popped out as nearly perfect circular rings of radio emission, huge, faint, and surprisingly circular, with very little corresponding optical light in most cases. They are enormous. Some are hundreds of thousands to millions of light-years across. What could make such a tidy ring? Various ideas include a giant shockwave from a past outburst of a central galaxy. Imagine a supermassive black hole flaring wildly in the past and sending a spherical wave through the surrounding gas, lighting it up in radio as it went, or an expanding shell from a massive starburst-driven wind, or even the radio lobes of an active galaxy seen end-on. No consensus has emerged yet, and ORCs are a perfect example of how new instruments can reveal phenomena that simply weren't on our radar before. Hani's Voorwerp is a different kind of oddball with a human story. In 2007, during the Galaxy Zoo citizen science project, a Dutch schoolteacher named Hani van Arkel noticed a strange green blob near a galaxy in an archive image and flagged it. Astronomers called it Hani's Voorwerp. Voorwerp means object in Dutch, and set about figuring out what the green glow was. Follow-up observations showed it was not a galaxy at all, but a cloud of gas glowing with strong emission lines of oxygen, and the cloud was too far from the nearby galaxy to be lit by its current activity. The leading explanation became a quasar light echo. The central black hole of the galaxy had been actively accreting and shining as a quasar in the recent past, illuminating the gas cloud. Since then, the quasar had shut off, but the light that left earlier was still traveling outward and lighting the cloud. Hani's Voorwerp gave us a real-time glimpse into the flickering behavior of black holes, and the fact that galactic nuclei can change their level of activity on surprisingly human timescales, tens of thousands of years, which is the blink of an eye in cosmic terms. Then there are the jellyfish galaxies, which get their name from the long, tentacle-like trails of gas and young stars that stream behind them as they plunge through the hot, dense gas of a galaxy cluster. Imagine a car driving through a rainstorm. The wind tears water off the back of the car, forming streaks behind it. Similarly, jellyfish galaxies suffer ram pressure stripping. The intracluster medium, a diffuse but extremely hot and thin plasma filling galaxy clusters, exerts pressure on a galaxy moving through it, peeling off gas. That stripped gas can form spectacular tails where star formation is triggered, creating luminous knots trailing behind the galaxy. ESO 137-1 is a dramatic example, visible in optical, X-ray, and infrared. Jellyfish galaxies are vivid demonstrations of environment shaping galaxy evolution. They show how being in a crowded neighborhood, a cluster, can transform a gas-rich spiral into a quenched, gas-poor system. Shell galaxies are another class of visually striking objects. Elliptical galaxies, which often look smooth and featureless, sometimes display faint, concentric shell-like structures in their outskirts. These shells are the fossil record of one or more small galaxies that were swallowed and torn apart by a larger elliptical. The stars from the smaller galaxy get placed on similar elliptical orbits and pile up at their turning points, creating ripples or shells. Systems like NGC 474 display multiple shells, like tree rings revealing a history of past mergers. These features are faint and require deep imaging to see, so advances in sensitive wide-field cameras have allowed astronomers to find many more such tidal fossils around nearby galaxies. Our own galaxy is no stranger to these scars. The Milky Way is surrounded by stellar streams, long, narrow ribbons of stars that are the shredded remains of dwarf galaxies and globular clusters ripped apart by our galaxy's gravity. The Sagittarius stream, for instance, is material torn from the Sagittarius dwarf spheroidal galaxy, which is in the process of being accreted by the Milky Way. The Gaia satellite, which measures positions and motions of stars with exquisite precision, has been a game-changer here, revealing dozens of streams and substructures in the galactic halo. These streams are like breadcrumb trails that tell us how large galaxies like ours grow by eating smaller ones. Another set of curious objects are the green pea galaxies discovered in the Sloan Digital Sky Survey by citizen scientists who noticed little greenish compact blobs. Their color comes from specific emission lines of doubly ionized oxygen that get redshifted into the optical filters used by the survey. Green peas are small, compact, and undergoing intense bursts of star formation, often with low metallicity, meaning they haven't been enriched much by older generations of stars. They are of broad interest because they may be local analogs of the tiny, vigorous galaxies that reionized the universe in its youth. Some green peas seem to leak ionizing radiation into intergalactic space, exactly the kind of behavior that would have helped reionize the early universe. So these odd-looking little blobs serve as laboratories for understanding cosmic dawn. Tadpole, Galaxies are another descriptive name. In deep Hubble images of the early universe, many galaxies look like tadpoles, a bright clump at one end with an elongated tail. These structures are common at redshifts when the universe was younger and galaxy collisions and bursts of star formation were more frequent. The tadpole shape can arise from gravitational interactions or from star formation propagating along the disk. They're another reminder that young galaxies were often messy and turbulent. All these peculiar shapes are not just curiosities, they are clues. They tell us about how gas moves, how stars are born and die, and how gravity sculpts structure over cosmic time. They reveal the ingredients and the environmental processes that make galaxies grow, die, merge, or lie dormant. The way astronomers piece these stories together is by combining information across the electromagnetic spectrum. Each wavelength gives a different clue. Optical images show starlight. Ultraviolet highlights the youngest, hottest stars and the places of recent star formation. Infrared sees cooler stars and dust, and can probe star formation obscured by dust that optical light misses. Radio telescopes map neutral hydrogen gas and sometimes molecular gas tracers like CO, which are the raw material for forming stars. X-rays reveal hot gas, either the very hot halos around clusters and massive galaxies or the energetic output of accreting black holes. Spectroscopy, spreading light into its component colors, gives velocities, chemical compositions, and relatedness. Are two pieces of sky actually at the same distance or just a chance alignment? And gravitational lensing provides a direct probe of mass, including the invisible dark matter, because it bends light regardless of whether that mass is luminous or not. Take the case of a suspected dark galaxy. You want to detect neutral hydrogen to see if there's gas. You want deep optical and infrared imaging to search for faint starlight. You want spectroscopy to measure motions and thus infer mass. And you want to map the environment, because if the gas is part of a tidal tail, you'll often find a plausible donor galaxy nearby. Similarly, with ring galaxies, you look for blue colors indicating young stars in the ring. You map gas to see if it's compressed. You look for a possible intruder galaxy, and you model the collision to see if the ring's velocity fits a ripple scenario. With Orcus or Hani's Vorwerp, you combine radio, optical, and X-ray observations to discriminate between shockwaves, relic radio lobes, or echoes of past quasar activity. Why put so much effort into cataloging and understanding oddballs? Because strange cases stress-test our theories. Cosmology and galaxy formation models are tuned to reproduce broad statistics: how many galaxies there are at different masses, how stars form, how galaxies cluster. But the outliers tell you where the model might be missing physics. Do we understand feedback, how stars and black holes inject energy back into gas and regulate further star formation? Do we treat environment correctly? How does being in a cluster change a galaxy's fate? How is dark matter distributed on small scales? Dark galaxies, ultra-diffuse systems, and the galaxies with anomalous dark matter content provide sharp probes of these questions. Looking ahead, the tools at astronomers' disposal are growing sharper and more plentiful. The James Webb Space Telescope, JWST, has opened windows into the infrared universe, allowing unprecedented views of faint, distant galaxies and their structure. Ground-based projects like the Vera Rubin Observatory, formerly LSSD, will survey the sky deeply and repeatedly, fishing out low-surface brightness features like tidal streams, shells, and faint outer disks. Radio observatories, particularly the SKA and pathfinders like ASKAP and Meerkat, will map the neutral hydrogen in vastly more galaxies, out to greater distances, and with far better sensitivity than before, a potential dark galaxy hunting revolution. The synergy of these facilities will let us test whether the dark blobs in radio maps are gravitationally bound systems or ephemeral debris, whether UDGS are stripped dwarfs or failed massive galaxies, and what processes control star formation suppression. At the same time, stellar surveys like Gaia are providing a detailed census of our own Milky Way's stellar components, exposing streams and substructures that are the fossil record of past accretion events. That information feeds back into cosmology. By understanding how often galaxies merge and what happens to stars and gas during those mergers, we refine the bigger picture of galaxy growth. It's tempting to move from the exotic back to the familiar and think the universe must be governed by simple, elegant rules that we'll soon write down. Reality is messier. Galaxies are subject to a suite of processes: gravity, gas dynamics, magnetic fields, radiation, feedback from stars and black holes, cosmic environment, and the balance between these factors can vary dramatically from place to place and time to time. The remarkable variety in the population, the ghosts, the rings, the jellyfish, the green peas, the orcas, reflects that complexity. Each oddball is an experiment run by the universe, often at scales and energies we can't replicate on Earth. Our job as observers and theorists is to interpret the outcomes. There are also human elements to this story. Citizen scientists help discover some of these oddities. Hanny's Vorwerp is the classic example, where a non-professional eye flagged something that automated pipelines would have missed or discarded. The green peas were also first noticed by citizen scientists. That's partly because the human eye and brain are excellent pattern recognition tools. When you're looking for needles in a universe-sized haystack, a crowd of volunteers eyeballing images can still beat a computer at spotting the weird and unexpected. That dynamic shows how technology and community can accelerate discovery. The search for dark galaxies also touches philosophical edges. We're trying to inventory not only what glows, but what has mass. Dark matter, that invisible component that dominates galaxies' mass budgets, remains one of the deepest puzzles in physics. If there are entire halos that never lit up with stars, they might be the cleanest environments in which to study dark matter. If they're rare or absent, that tells us dark matter halos don't exist in a vacuum. Baryons, gas, and stars leave fingerprints on their evolution from the start. Either way, probing the dim and the strange refines our map of the unseen. What if, in some future survey, we find dozens of genuine dark galaxies, objects with rotating hydrogen and gravitational evidence of mass but no stars, isolated in otherwise quiet space? That would reshape how we think about the population of dark matter halos and the physics of star formation. Alternatively, if most candidates turn out to be tidal debris, that tells us interactions are extremely effective at shuffling gas around, and that the apparent darkness is more a matter of timing and environment than a fundamental state. Either outcome is instructive. Similarly, ring galaxies and shells remind us that galactic encounters are both destructive and creative. They rip, mix, and often spark fresh star formation. A head-on collision can produce a ring that lights up with young stars, transforming matter into a new generation of suns. On longer timescales, these events feed the growth of larger galaxies and sculpt their morphology. Observing rings at different stages and modeling their kinematics allows astronomers to reconstruct the impact parameters and timescales of collisions. In a sense, doing cosmic forensics. The bizarre structures like orcs and large-scale radio rings also highlight that the sky still hides phenomenology we don't fully understand. Every time astronomers have built a new instrument that maps the sky in a new way or with greater sensitivity, the universe has produced surprises. The more eyes we put up, across radio, optical, infrared, X-ray, and gamma-ray, the more oddities we find. Some of these will resolve into known physics with a better model. Others may point to new processes or overlooked mechanisms. That is where the thrill lies. The universe keeps generating puzzles that force us to expand our toolkit and sometimes our imagination. As you read about these strange galaxies, it's worth remembering scale. Many of these structures span tens to hundreds of thousands of light years, enormous on human terms. The processes shaping them can take millions to billions of years. Yet we catch them at the right stages to learn about critical transitions. A ring just after a collision, a jellyfish in mid-ram pressure stripping, a halo before it formed stars, a shell shortly after a merger. We are not watching in real time like a nature documentary with continuous coverage. We are seeing snapshots from across cosmic history and stitching them together into plausible life stories. That's a detective story where the clues are faint and multi-wavelength, and where new instruments and clever people keep filling in the blanks. If you enjoy the weirdness of the cosmos, the current era is an embarrassment of riches. The combination of citizen science, massive surveys, and ever more sensitive telescopes means we'll keep discovering more oddballs, more ringed jewels, and more potential dark islands. Each discovery is a prompt to ask, what processes made this object? What does it tell us about the physics of gas, stars, and dark matter? How common are objects like this, and what role do they play in the larger cosmic ecosystem? So the next time you scroll through a gallery of galaxy pictures or glance at a sky map in a podcast, remember the messy truth behind those images. Galaxies are not uniform. They are the products of histories, sometimes quiet, sometimes dramatic. The most mysterious ones are the best teachers because they expose limits in our understanding. They force us to improve our observations, refine our simulations, and, occasionally, rewrite a chapter of cosmic history. The universe is full of ghosts and rings and things that look like they came from another handbook. Teasing out their stories is one of the great continuing adventures of modern astronomy. If the universe likes to surprise us with ghostly clouds and perfect rings, it delights even more when it hands us galaxies that seem to be living in the wrong chapter of cosmic history. Some galaxies are mysteriously enormous for how early they appear, others are wrapped in dust so thick they hide their own light, and a few look like the cores of big galaxies that got stripped down to a dense husk. These cases aren't just pretty pictures, they push on the edge of our theories and force us to refine how we think galaxies grow and change. Start with the ones that seem to have arrived too early. Telescopes act like time machines. When we look farther away, we look back in time. For decades, astronomers used that trick to map how galaxies assembled. The standard picture says that small fluctuations in the early universe grew under gravity into dark matter halos. Gas fell in, cooled, formed stars, and over hundreds of millions to billions of years, those clumps merged into bigger galaxies. It's a gradual climb. So when we find a galaxy that looks massive and well-formed at an epoch when the universe was only a few 100 million years old, we pay attention. A few examples have become shorthand for the puzzle. GN's 11, first identified in deep Hubble imaging and later studied with improved spectroscopy, is a galaxy seen when the universe was only about 400 million years old. It is surprisingly bright for its age. Then, with the launch of the James Webb Space Telescope, astronomers began reporting more candidates that could be even earlier and, in some cases, more massive than expected. Those reports created headlines because if the masses and ages hold up, our standard models have to either make stars form much faster or find a way to put an awful lot of stellar mass into place very quickly. Why is that challenging? Building a massive galaxy is like building a city. You need raw materials, a workforce, and time. In cosmic terms, the raw material is gas, and the workforce is stars that form from that gas. But stars themselves don't make new stars, so you need conditions that are efficient at turning gas into stars early on. The time available in the early universe is short. Also, forming a massive galaxy requires a relatively massive dark matter halo to gather and hold that much gas. Our simulations show how halos grow, and while some fluctuations can be large, truly massive halos at extreme early times should be rare. So when several candidates crowd that regime, you wonder whether something basic in the simulations or in how we infer mass from light is off. There are many ways out of the paradox that don't require changing physics overnight. For one thing, translating an observed brightness into a stellar mass depends on assumptions about the star's ages, how fast they formed, and how much dust is hiding some of the light. Young, hot stars are very bright for their mass. A burst of recent star formation can make a galaxy look surprisingly massive for a short while. Dust can hide starlight shortward of certain wavelengths, throwing off mass estimates unless you account for it. There's also the initial mass function, a technical term for the mix of star masses a galaxy produces. And if that mix was skewed in the early universe toward more massive, luminous stars, the same amount of mass could shine more brightly. Finally, some of the brightest candidates might be magnified by gravitational lensing, the gravity of a foreground galaxy cluster bending and amplifying the light from a more distant object, making it appear brighter and therefore, without correction, more massive. Astronomers are cautious and methodical. Spectroscopy, breaking the light into its component colors, gives more reliable distances and some clues about ages and dust, but it's expensive in telescope time, especially for faint objects. JWST has already given spectra for some distant objects, confirming some redshift estimates, but also showing that a few earlier candidates need rethinking. The debate feels alive because it matters. If a real population of very massive, very early galaxies exists, we learn that star formation recipes in the first few 100 million years can be different, or that halos grew faster than our models predict, or even that some new mechanism, like huge black hole-driven feedback or early direct collapse black holes, played a role in seeding these systems. That brings us to another extreme: supermassive black holes in the early universe. Quasars, galaxies whose centers glow enormously because gas is falling onto a supermassive black hole, have been detected at astonishingly early times, some less than 1 billion years after the Big Bang, with black hole masses of hundreds of millions to billions of suns. Growing a black hole that large so fast is not easy under ordinary accretion rates, so theorists have proposed a few workarounds. Black hole seeds that start off larger, for example, from the direct collapse of a giant gas cloud rather than from the death of a single massive star. Periods of rapid, super-Eddington accretion, brief phases, when a black hole feeds faster than normally allowed by simple radiation pressure arguments, or repeated mergers of massive black holes. Each path has hurdles, but the observational facts, bright quasars so early, motivate creative solutions. These early black holes don't just grow in isolation. Their outbursts can pump energy into their host galaxies, heating gas and suppressing star formation, or driving winds that sweep gas out. That feedback plays into the broader question of how galaxies quench their star formation and when. On the topic of hidden light, not every intense star-forming galaxy announces itself in the optical. Some are cloaked in dust, and when dust warms by starlight it glows at far infrared and submillimeter wavelengths. In such galaxies, most of the ultraviolet light from young stars is absorbed by dust and re-emitted at longer wavelengths. These dusty starbursts include the so-called submillimeter galaxies, SMGS, and ultraluminous infrared galaxies, ULIRGS. In local universe terms, ARP 220 is a famous example. It looks messy in optical images, a pair of merging nuclei surrounded by dust, but it's extraordinarily luminous in the infrared, with star formation rates that can be hundreds of suns per year, far above that of a normal spiral like the Milky Way. SMGs were originally discovered in the 1990s with early submillimeter cameras, and they turned out to be mostly high redshift, highly dust-obscured galaxies undergoing extreme bursts of star formation. How do they make so many stars so fast? Often the answer is mergers and interactions. Two gas-rich galaxies collide, the gas funnels toward the center, and a catastrophic burst of star formation ensues, possibly accompanied by a hidden quasar. These bursts can be powerful enough to change a galaxy's fate, consuming large gas reservoirs or driving winds that expel the gas, leaving a quenched, compact remnant. Observations across wavelengths, radio to infrared to millimeter, help tease apart the dust and measure the star formation rates and the amount of obscured activity. Instruments like ALMA, the Atacama Large Millimeter/Submillimeter Array, are crucial here. Their sharp eyes reveal the compact regions where most of the action happens and show that these starbursts can be surprisingly compact and intensely star-forming. Then we have the so-called Lyman alpha blobs, or LABS, which look like enormous, glowing clouds of hydrogen emission in the ultraviolet line known as Lyman alpha. These blobs can be hundreds of thousands of light-years across, orders of magnitude larger than a normal galaxy, and they often live in protocluster regions where many galaxies are forming simultaneously. What powers the glow? That's an open question with multiple plausible answers. One idea is that intense star formation or an active galactic nucleus ionizes the gas, which then recombines and produces the Lyman alpha glow. Another is that cold gas streams falling into a forming galaxy can radiate away energy as they cool, cooling radiation, producing extended emission. Resonance scattering complicates the picture. Lyman alpha photons scatter off neutral hydrogen many times before escaping, which can make the emission appear much more extended than the original source. Labs are laboratories for studying gas flows during the assembly of massive structures and for teasing out the interplay between galaxies and their gaseous surroundings. Not every odd galaxy is large. Some punch well above their weight in compactness and mass. Astronomers have found compact massive galaxies, nicknamed red nuggets, at redshifts around 2, when the universe was only a few billion years old. These objects are small in size, often only a few thousand light-years across, but contain as much mass as a much larger galaxy like the Milky Way. They are mostly old, red stars, meaning they formed their stars quickly early on and then shut down star formation. The surprise came when astronomers looked for such dense relics today and expected most of them to have grown by mergers into modern ellipticals. A handful, however, seem to have survived relatively untouched to the present day. NGC 1277, for example, is sometimes called a relic galaxy because it has an extremely compact, dense stellar population and hosts an unusually massive central black hole compared to its stars. These relics invite questions. What environment or history allowed them to stay so compact? Did they live in the center of a region that didn't suffer many mergers, or were they protected somehow? Studying them helps reveal the diversity of evolutionary paths galaxies can take. At the opposite size extreme from red nuggets are ultra-compact dwarfs, UCDS, and compact ellipticals like M32, which sit between the scales of globular clusters and small galaxies. Their origins are debated. Are they the remnants of larger galaxies stripped down to their dense cores by interactions with a bigger neighbor, or are they simply the high-mass tail of star cluster formation? The strip core idea explains some UCDs that show evidence of extra mass in their centers, perhaps a central black hole that wouldn't be expected if they were merely oversized star clusters. Finding such black holes changes how we see galaxy assembly, because it implies that tidal interactions can leave behind tiny, but massive fossils that still tell the story of a once larger galaxy. Speaking of stripping, tidal dwarf galaxies occupy an odd niche. When big galaxies interact and fling out long tails of gas and stars, sometimes the clumped material in those tidal tails can collapse and form a small, self-gravitating object, a new, tiny galaxy born from the debris of its parent. In theory, these tidal dwarfs might be poor in dark matter, because tidal tails are made mostly of the outer, baryon-rich parts of galaxies rather than the halo-dominated core. Observationally, disentangling whether such dwarfs truly lack dark matter is challenging. Measuring the internal motions of faint stars is hard, but if confirmed, tidal dwarfs would be an intriguing exception to the usual rule that galaxies form inside dark matter halos. They are reminders that galaxy formation is not just a bottom-up process dictated solely by dark matter. Baryonic physics, gas dynamics, collisions, and star formation can sometimes make galaxies in their own right. Galaxies also undergo dramatic personality changes. Many spiral galaxies at earlier times were gas-rich and actively forming stars. Many of today's massive ellipticals are quiescent, having stopped forming stars long ago. The process of shutdown, quenching, has several suspects. One major actor is feedback from active galactic nuclei. As gas falls onto a central black hole, the resulting energy output can heat or expel gas, preventing further star formation. Another is environmental influence. A galaxy falling into a cluster can have its gas stripped by the hot intracluster medium, ram pressure stripping, leaving it gas-poor and unable to continue forming stars. Jellyfish galaxies we talked about earlier are dramatic examples in action. Stellar feedback, winds and supernova explosions from massive stars, can also heat and push gas around, regulating star formation in smaller galaxies. The balance of these effects depends on galaxy mass and environment. Understanding quenching is essential because it explains why some galaxies are still blue and forming stars, while others turn red and passive. There are also galaxies that seem to undergo sudden, violent shifts. Post-starburst galaxies, sometimes called E-plus-A galaxies, appear to have formed a large fraction of their stars in a sudden burst that then abruptly stopped. Their spectra show strong signatures of a type stars, young, luminous stars, but little ongoing star formation. These galaxies are thought to be the aftermath of mergers or interactions that triggered a rapid burst and then exhausted or expelled the gas. They are transient, living only a few 100 million years in this state before their young stars age, and the galaxy fades into an older population. Catching galaxies in this phase gives a snapshot of a transformational period in their life. Another layer of oddness comes from gas flows on larger scales, the circumgalactic medium (CGM) and the intergalactic medium (IGM) that surround and thread galaxies. Observations show that galaxies don't exist in isolation. They accrete gas from their surroundings and expel it via winds. This circulation controls how much gas is available to form new stars. Mapping these flows is difficult because the gas is often diffuse and faint, but clever tricks, using bright background quasars as flashlights to see absorption signatures of gas in intervening halos, or directly imaging emission from diffuse gas in specific lines, have revealed that halos are full of structure. Cool clumps, warm ionized filaments, and hot X-ray emitting gas. Sometimes you get enormous, faint filaments of ionized gas connected to galaxies or groups, revealing interactions and past outflows. These extended gaseous reservoirs are crucial for understanding why some galaxies fuel sustained star formation, while others run out of gas. When astronomers talk about mysterious galaxies, they also mean objects with odd motions or weird mass distributions. The missing satellites problem is an old example. Numerical simulations of dark matter predict lots of small subhalos around a Milky Way-sized galaxy, but for a long time astronomers found far fewer dwarf satellites than expected. Improved observations and the discovery of many faint dwarfs, especially with surveys like SDSS, Sloan Digital Sky Survey, and more recently with deep imaging from telescopes like the Dark Energy Survey and the Rubin Observatory coming online, have reduced the tension, but questions remain about the detailed distribution and internal structure of these dwarfs. Some dwarfs show cores in their mass distribution, flatter inner density profiles, while cold dark matter simulations tend to predict cusps, steep cores. This mismatch has led to suggestions that baryonic processes, like stellar feedback that can move dark matter around, flatten cusps into cores, or to more adventurous ideas that dark matter might have self-interactions that change its distribution on small scales. Observations of the faintest galaxies and their internal motions remain a key test. The satellites around the Milky Way and around Andromeda have also raised another puzzle. The apparent alignment of many satellites in a thin plane rather than a random, spherical distribution. If this planar arrangement is real and common, it could be a sign that satellites are brought in along filaments, or the result of tidal interactions that create satellites from debris. The statistical significance and ubiquity of such planes are still debated, and better data and careful modeling are needed. But the idea that the arrangement of satellites could be telling us about the cosmic web and the history of infall is a neat example of how shapes and alignments carry information. There are also galaxies that flout expected relationships. For decades, astronomers noticed tidy correlations. More massive galaxies tend to have more massive black holes, brighter galaxies often have faster-moving stars, and so on. These correlations aren't perfect, of course, and the outliers are especially interesting. We already mentioned NGC 1277 with its overlarge black hole. Another intriguing case is MADI 7, whose central black hole is enormous and was imaged by the Event Horizon Telescope. These over- or undermassive black holes relative to their hosts suggest diverse growth histories. Maybe the black hole grew rapidly early, maybe the galaxy lost mass later, or maybe feeding and growth are episodic and decoupled from the galaxy's stellar growth. Understanding the scatter in these relationships teaches us how central black holes and galaxies co-evolve. On the observational frontier, new techniques keep turning up surprises. Deep, wide-field imaging reveals faint tidal streams around many nearby galaxies, the fossilized remains of cannibalized dwarfs. The Gaia satellite revolutionized our picture of the Milky Way's structure by providing precise motions for over 1 billion stars. That data has exposed unexpected substructures and revealed that the Milky Way had a major merger in its past, a collision now known as Gaia Enceladus or the Gaia sausage, which contributed many stars to the inner halo. Such archaeological work is like peeling layers from a planet to find its history written in rocks. In the galaxy's case, the star's motions and compositions record past mergers, bursts of star formation, and migration. Another kind of peculiarity lies in the way galaxies light up in certain emission lines. We mentioned green peas earlier. Related to that are extreme emission line galaxies that have very strong, narrow lines from ionized gas. Because these lines are so prominent, they serve as beacons, helping us find small, vigorously star-forming galaxies at different cosmic times. These systems are often low in heavy elements, what astronomers call low metallicity, which makes them resemble the likely properties of early galaxies. Studying them gives a laboratory for processes like the escape of ionizing photons, which mattered for the reionization of the universe. On a completely different observational front, the radio sky keeps providing the unexpected. We touched earlier on odd radio circles ORCES, vast, circular radio features discovered in new, sensitive radio surveys. Their clean geometry and large sizes are puzzling. Are they rings of shocked gas from a past AGN outburst? Are they the end-on view of radio lobes or bubbles blown by a central engine? Do they trace ancient galaxy collisions? Each hypothesis has pros and cons, and ORCES are a great reminder that the radio window still contains phenomena we barely knew to look for until instruments matured. And beyond electromagnetic observations, we're entering an era where other messengers, gravitational waves and neutrinos, will increasingly speak to galaxy formation. Merging black holes and neutron stars emit gravitational waves, and while the loudest events seen so far are stellar mass mergers, future observatories like LISA, Laser Interferometer Space Antenna, aim to detect gravitational waves from merging supermassive black holes. Those mergers are the endgame of galaxy collisions, and detecting them will provide direct information about how often big galaxies merge and how black holes pair up and coalesce. High-energy neutrinos and cosmic rays, although rarer messengers, also tie into the most energetic galactic processes like jets from active black holes and powerful starburst-driven shocks. There's also an element of serendipity and human pattern recognition in many discoveries. Citizen scientists played a starring role in spotting oddities like Hani's Vorwerp and the green peas. Even in the age of sophisticated algorithms, human eyes and intuition sometimes find things machines miss or flag surprising patterns worth a second look. As surveys grow larger and produce millions of images, humans and algorithms will increasingly work together. Machines to sift the obvious candidates and humans to investigate the peculiar ones that don't fit automated criteria. One more thread we should pull on is the idea of failure modes in galaxy formation. Just as engineers study why machines fail, astronomers study why some dark matter halos fail to produce many stars. The dark galaxies we discussed earlier and the ultra-diffuse galaxies that look like they might be failed giants. Examining these failures helps isolate which physical processes are essential for making stars. Is it the heating from the ultraviolet background at early times that prevents gas from cooling in small halos? Is it early feedback from the first generations of stars? Or is it environmental? Does living near a massive neighbor rob a small halo of its gas? Connecting these questions with observations, searching for gas-rich but star-poor halos in neutral hydrogen surveys, modeling the effect of reionization, and tracing the distribution of ultra-diffuse galaxies in clusters and the field, tightens the feedback loops between theory and data. Finally, it's worth noting that every new facility changes the balance of what we can see, and therefore what we think is rare or common. Before deep surveys and sensitive instruments, many odd classes were missing simply because we couldn't detect them. Now, with instruments like JWST, ALMA, large optical surveys, and next-generation radio arrays, what looked like exotic minorities may turn out to be crucial stages or common outcomes under certain conditions. The more we look, the more varied the population appears to be, and the more arrows we have to test theories. So we keep collecting the odd, the extreme, and the unexpected. Galaxies that look too old, too young, too massive, too empty, too ringed, or too faint. Each case prompts a deeper look, more wavelengths, better spectra, sharper images, and more refined models. In many ways, the strangest galaxies are the most informative because they illuminate the edges of our understanding and help reveal the physical principles at play across cosmic scales. To move from cataloging curiosities to understanding them, astronomers lean heavily on models and simulations. Think of this like building a virtual universe in a computer. You set up the basic ingredients, dark matter, gas, gravity, and the rules for how gas cools and how stars and black holes form and feed back energy. Then you watch how structure grows over billions of years. It's a bit like baking with a complicated recipe where some ingredients you know exactly, like gravity, while others, how exploding stars stir gas or how radiation pressure moves dust, you only approximate. Those approximations matter. They are the places where the simulations can either shine or mislead. Why use simulations at all? Because some processes happen on scales far too large or small to experiment with directly. We can't wait a billion years to see a galaxy evolve, and we can't create a galaxy in a lab. So we test physical recipes inside virtual universes, compare their galaxies to what we observe, and adjust. When a simulation produces similar-looking populations of galaxies, the right numbers at the right masses, and with comparable colors and sizes, it bolsters confidence that the included physics captures the main drivers of galaxy growth. When it doesn't, the failures point to missing or misrepresented physics. A major challenge in simulations is scale. The universe cares about everything from the motion of individual stars and supernova explosions to the gravity of dark matter on million light-year scales. Computers can't resolve that full range at once, so modelers use subgrid recipes. They don't simulate each supernova or each star, but they add rules that capture the average effect of many such events on the surrounding gas. Think of it like weather forecasting on a global scale. You can't model each cloud, so you adopt effective rules for how heat and moisture behave on small scales and let the large-scale model use those rules. Different groups make different choices for those rules, and that leads to different answers for the same initial conditions. Those choices have concrete consequences for the oddball galaxies we care about. Ultra-diffuse galaxies, UDGS, for example, can arise in multiple ways in simulations. In some runs, violent internal feedback, repeated bursts of star formation that send gas cavorting out of the galaxy, puffs up the stellar distribution, and can produce a faint, extended object that resembles observed UDGs. In cluster environments, tidal heating and repeated interactions with neighbors, and the cluster's tidal field can also stretch an originally ordinary dwarf into a fluffy UDG. Both channels may exist in nature, and models tuned to include strong feedback or to account for environmental harassment can produce UDG-like objects. But the relative importance of these processes, whether most UDGs are puffed-up dwarfs or failed giants, remains debated, and observations targeted at stellar populations, globular cluster counts, and dark matter content help discriminate between the scenarios. The dark galaxy question ties into another deep topic: how reionization and the ultraviolet background affect the ability of small halos to form stars. In the early universe, the first stars and quasars flooded space with ionizing photons that heated the intergalactic gas. Tiny halos below a certain mass threshold struggle to capture and cool that hot gas, so they fail to form stars. Simulations that include the timing and intensity of reionization naturally predict many dark or nearly dark halos, more small halos than luminous dwarf galaxies. Observationally, hunting those failed halos is exactly what neutral hydrogen surveys are doing. If you find a rotating H-high blob with a mass signature but no stars, that would be a neat confirmation. So far, many candidate dark galaxy detections have been reinterpreted as tidal debris or transient features, but future, deeper surveys may find bona fide examples. The answer, whether dark halos are abundant or rare, feeds back into cosmological models and into how we conceive of the smallest structures in the cosmic web. When simulations fall short, theorists sometimes consider modifying the dark matter itself. The standard cosmological model, lambdictum, cold dark matter plus a cosmological constant, predicts a wealth of small dark matter clumps and steep inner density cusps in dwarf halos. Observations hinted at fewer satellites and shallower inner densities, which spawned ideas like warm dark matter, WDM, where dark matter particles have a small thermal velocity that smooths out small-scale structure, or self-interacting dark matter, SIDM, where dark matter particles scatter off each other and create cores instead of cusps. These aren't ad hoc moves, they're concrete hypotheses that make distinct predictions. For instance, SIDM tends to make inner density profiles rounder and can alleviate some tensions in dwarf galaxies. WDM suppresses the formation of the smallest halos, potentially reducing the number of expected satellite galaxies. Observers now test these ideas by measuring the abundance and internal structure of the faintest galaxies, the presence or absence of tiny dark clumps through lensing, and the dynamics of stellar streams, which can be perturbed by invisible lumps. So weird galaxies can be the probe that distinguishes between different flavors of dark matter. The case of the NG cone 1000 and 52D, F2O and D, F4 pair illustrates how careful crosschecks are critical. Initial measurements of the velocities of star clusters around D F2O suggested a surprisingly low velocity dispersion, implying little dark matter. That was headline-grabbing, because it seemed to contradict the conventional wisdom that stars sit inside massive dark matter halos. But the result hinges sensitively on distance. If the galaxy is farther away than assumed, its luminosity and physical size change, and the inferred dark matter content alters. Follow-up measurements revise distances and dispersions in different ways, and the community remains split on the interpretation. This episode highlights an essential point: unusual claims require robust, multi-method confirmation. Spectroscopic redshifts, distance indicators, high-quality velocity measurements, and environmental context all matter before we rewrite the textbooks. Another domain where models and observations clash and inform each other is in the early universe. The bright, massive galaxies and the billion solar mass black holes seen at very high redshift have driven debates about how quickly structures can assemble. Simulations typically build galaxies from the bottom up, with small objects merging and growing over time. Producing abundant massive galaxies very early can strain those prescriptions. But models have several levers to pull: the efficiency of star formation, the initial mass function, the distribution of stellar masses, the presence of heavy seeds for black holes, and the role of mergers, among others. Some recent simulation suites have explored scenarios with bursts of extremely efficient star formation in dense gas clouds, or the rapid formation of large black hole seeds through direct collapse of gas, both of which ease the tension. The point is not to claim a single right answer yet, but to show how observations force modelers to explore a broader parameter space and to test alternative physical pathways. Observational technique matters as much as the models. A classic pitfall is selection bias. What we find depends on how we look. Many galaxies are intrinsically faint in surface brightness, meaning their light spreads thinly across large areas. Traditional surveys tuned for compact, bright objects miss these ghosts. That's one reason UDGs and diffuse tidal features came into focus only as cameras and data processing got better at preserving low surface brightness light. Similarly, radio telescopes have only recently had the sensitivity and survey speed to reveal large-scale diffuse, high clouds and features like the odd radio circles. Malmquist bias, the tendency for brighter objects to be overrepresented in a flux-limited sample, skews our census unless corrected. Sophisticated surveys now model these effects, but interpreting outliers still demands an awareness of how detection limits shape what we call rare. Distance measures are another recurring difficulty. Photometric redshifts, estimates based on a galaxy's color measured through several filters, are useful for huge samples, but can be uncertain for odd objects with unusual colors or heavy dust obscuration. Spectroscopic redshifts, which identify specific spectral lines, are definitive but costly in telescope time. Misestimating a galaxy's distance can lead to misinterpreting its size, luminosity, and mass. That's why spectacular claims often require spectroscopic confirmation. It anchors the entire physical picture. New instrumentation has changed what we can detect and characterize. Integral field spectrographs, IFUs, which take spectra across an object's image, let astronomers map velocities and chemical compositions pixel by pixel. That has been a game changer for ring galaxies and collisional systems. IFU maps can show how gas and stars are moving in the ring, revealing whether the motion is consistent with an expanding wave from a collision or with resonance-driven inflow. Instruments like MUSE on the Very Large Telescope have been particularly effective at revealing faint Lyman alpha emission around high redshift galaxies and dissecting the glowing nebulae in protoclusters. On the radio side, arrays like MeerKAT, ASKAP, and ultimately the SKA provide wide-field, sensitive maps of neutral hydrogen, which is the raw fuel for star formation. ALMA unlocks cold molecular gas at high angular resolution, showing where the star-forming material sits even in dusty, obscured galaxies. Interpreting the wealth of data requires new computational and statistical tools. Machine learning and advanced pattern recognition algorithms are becoming essential for sifting through millions of images and spectra to flag anomalies. But here again, there's a human factor. Citizen scientists played key roles in discovering some of the most famous oddities, like Hani's Vorwerp and the green peas. Humans are remarkably good at noticing patterns machines miss, especially in the early stages when we don't know what to parameterize. The most effective approach increasingly pairs algorithmic filtering to handle the obvious bulk and crowdsourced human inspection to highlight the genuinely weird. As datasets balloon, these hybrid human-machine systems will be crucial for finding the next class of unexpected objects. Odd galaxies also force us to ask about timescales. Many features are transient on cosmic stages. A ring produced by a head-on collision remains bright for a few 100 million years before star formation peters out and the structure dissolves. A quasar can flicker on and off over somewhat shorter durations, and we might catch its light illuminating a gas cloud, like Hani's Vorwerp, long after the central engine has dimmed. Tidal streams from a disrupted dwarf can remain visible for several billion years in a low-noise environment, but in a busy neighborhood, they might be quickly mixed and erased. Realizing which stage we're observing is essential for reconstructing a galaxy's life story rather than assuming the present snapshot is a stable, unchanging state. That temporal perspective is also why statistical samples matter. One spectacular case study can teach a lot, but astronomers want patterns, distributions of properties across hundreds or thousands of systems, to draw robust conclusions. Is GN11 an oddball or part of a larger population of early massive galaxies? Are Orcus the tip of an iceberg of radio relics or rare singular events? Large surveys, repeated observations, and careful follow-up build those samples and allow scientists to separate cosmic coincidence from systematic effects. Environment repeatedly shows up as a decisive factor in galaxy weirdness. The life cycle of a galaxy in a cluster is very different from one in a low-density field. In clusters, ram pressure stripping, tidal forces, and harassment by repeated high-speed encounters can strip gas, truncate disks, and create jellyfish galaxies or UDGs. In the field, isolated galaxies can quietly accrete gas from the intergalactic medium, fueling sustained star formation, and sometimes creating extended, cold gas reservoirs that look peculiar but are stable for long periods. The cosmic web, the network of filaments and nodes that connect galaxies, channels inflows and can preferentially feed galaxies along certain directions, imprinting alignments and anisotropies. So when astronomers see an odd galaxy, one of the first questions is, what neighborhood does it inhabit, and what does that environment imply about its past interactions and future? There is also an ongoing interplay between small and large-scale processes. Take feedback from supermassive black holes. On scales of parsecs, accretion disks and jets form and operate under extreme conditions. The energy they release can propagate outward in the form of winds and radio jets, interacting with gas on kiloparsec and larger scales, heating or expelling it, and impacting star formation galaxy-wide. Modeling how a compact, energetic engine couples to diffuse gas across many orders of magnitude and scale is hard, but it's necessary to explain things like quenched massive galaxies and the cavities observed in the hot gas of galaxy clusters that align with radio lobes. Observations that map these cavities, the associated radio emission, and the thermal state of the surrounding gas provide key constraints that force theorists to refine how feedback operates. Some of the most exciting frontiers involve linking different cosmic messengers. Gravitational waves, for example, don't directly show us a galaxy's stars or gas, but they do tell us about the invisible dance of compact objects. Future detectors like LISA aim to catch the low-frequency gravitational waves from merging supermassive black holes, the ultimate signpost of major galaxy mergers. If LISA detects such events and we can associate them with electromagnetic counterparts, we'll have a dramatic, multi-messenger view of how galaxy collisions proceed and how black holes grow and coalesce. Similarly, high-energy neutrinos and cosmic rays trace the most extreme particle accelerators in the universe, places like jets from active galactic nuclei or the shocks in starburst galaxies. Pinning down the origin of these messengers and linking them to particular galaxy types can reveal the energetic side of galaxy evolution. There's a philosophical but practical point here. Odd galaxies are not merely anomalies to be catalogued and forgotten. They are tests of the extremes. When a theory explains the bulk population but fails on the margins, those margins often expose the missing physics. Consider how the missing satellites issue led to decades of work refining both observations and theory, producing predictions about ultra-faint dwarfs and prompting searches that uncovered many new satellites around the Milky Way. Or think of how the discovery of powerful, dusty starbursts at early times led to detailed models of merger-driven star formation and feedback. Outliers catalyze progress. All this makes the ongoing flow of data and the development of instruments crucial. The Rubin Observatory will flood us with time-domain optical data, revealing variable galactic nuclei, transient starbursts, and tidal disruptions in previously unimagined numbers. JWST continues to peer deeper into cosmic dawn, testing our ideas about the first galaxies and their growth. SCA and its precursors will build unmatched HI maps, seeking the reservoirs and streams of neutral gas that feed star formation and searching for genuine dark halos. Meanwhile, more sensitive X-ray observatories and radio arrays will chart the energetic feedback processes that regulate galaxy growth. Together, this observational push will generate the statistics needed to move from anecdote to understanding. Finally, there's an element of patience and humility in all this work. The universe runs on timescales that dwarf a human lifetime, and we only see snapshots. But by combining those snapshots from different galaxies, different environments, and different epochs, and by building virtual universes where we can tweak the rules, scientists assemble plausible life stories for even the weirdest objects. The most mysterious galaxies are therefore not just puzzles to solve for their own sake. They are beacons that illuminate the physics of gas, stars, and dark matter under conditions we can't replicate on Earth. They tell us where our models succeed and where they need to grow. And every new oddball that appears in survey data is an invitation to refine our picture of how the cosmos builds complexity out of simple physical laws. If all of this leaves you wondering how astronomers actually decide between competing explanations, the short answer is, with a battery of complementary measurements that each probe a different piece of the puzzle. Think of a mysterious galaxy as a crime scene. Some clues are fingerprints, the motions of stars and gas. Some are chemical traces, what elements are present and in what proportions. Some are the neighborhood context, who the nearby galaxies are and how crowded the street is. And some are energy footprints, X-rays, radio jets, hot gas. No single measurement usually gives a definitive verdict. It's the pattern across all of them that points to the most plausible story. A key first move is to pin down the distance. If you misjudge how far away something is, you misestimate its physical size, luminosity, and mass. For many faint objects, we rely on spectroscopy, measuring specific features in the light that are shifted by the universe's expansion. Emission lines like hydrogen's H-alpha or oxygen lines, or absorption features from stars, give precise redshifts. But spectroscopy is expensive. It takes time on big telescopes, and the faintest, dustiest, or most diffuse targets can be very hard to get spectra for. That's why follow-up campaigns are triaged. Candidates that are most likely to overturn current understanding get the most aggressive follow-up. Once distance is secure, measuring mass is the next priority, because a great many of the strange behaviors reduce to mismatches between how much light is seen and how much gravity seems to be present. There are several independent methods to estimate mass. Rotation curves, how orbital speed changes with radius, are classic for disk galaxies. Map the velocity of gas, often via the 21 cm neutral hydrogen line or ionized gas with optical emission lines, and you can infer the gravitational potential that keeps that gas on its orbits. For spheroidal systems, where organized rotation is weak, astronomers measure velocity dispersion, how fast stars or globular clusters move randomly within the system. Higher random speeds imply a deeper gravitational well. Strong gravitational lensing, when a massive foreground object bends the light of a background source, gives a mass measurement that is independent of whether the object emits light at all. Finally, X-ray observations of hot gas can reveal a deep potential well. Gas sitting in a massive halo will often be heated to millions of degrees and glow in X-rays. Each method has limitations and systematics, so converging evidence is important. That's especially true for putative dark galaxies. If you think you've found a mass concentration with little or no starlight, you want to see consistent signals. An ordered velocity pattern showing rotation, a mass estimate from kinematics that matches the observed motion, and an absence of older stellar populations in deep optical and infrared imaging. You also want to check metallicity. Gas stripped from a large galaxy tends to be metal-enriched, while truly primordial or isolated halos might show very low metallicity. So measuring the chemical fingerprint of the gas via spectroscopy can help determine whether the gas was torn from a neighbor or is more pristine. Finally, the environment matters. If a hydrogen cloud is embedded in a messy region full of companions and tidal tails, it's more likely debris. If it's isolated in a quiet region, the dark halo hypothesis gains traction. Tidal debris and truly dark halos can be hard to distinguish because gas dynamics are messy. A tidal tail can mimic rotation if looked at in projection, and a transient condensation in a larger stream can appear gravitationally bound for a time. That's why time and context are important. Mapping the larger spatial environment, how gas and stars are distributed across tens or hundreds of kiloparsecs, reveals whether candidate objects are part of larger coherent structures. Wide-field radio surveys like those done by ASKAP, Meerkat, and the FutureSCA give those maps in HI, while deep optical imaging from instruments optimized for low surface brightness light, Dragonfly specialized pipelines on big telescopes, reveal the faint stellar counterparts or tidal streams that betray a tidal origin. For ultra-diffuse galaxies, UDGS, the approach is similar but with different practical hurdles. These galaxies are low in surface brightness, which makes them faint against the sky and susceptible to being measured in brightness and size. Astronomers use specialized techniques to measure their structural parameters reliably. Careful sky subtraction, stacking of multiple exposures, and using large aperture telescopes designed or optimized to preserve faint extended light. The question of whether a given UDG is a bloated dwarf or a failed giant often revolves around its globular cluster population and its dark matter content. Massive galaxies tend to host many globular clusters. If a UDG has an unusually rich globular cluster system, that suggests a more massive halo than its starlight alone would imply. Measuring the dynamics of those clusters can then give an independent mass estimate. This trick was crucial in the analysis of Dragonfly 44, where the globular cluster counts initially suggested a very massive halo. Distance uncertainties also loomed large in the DF2/DF4 debate. Here, the measured velocities of globular clusters suggested a very low velocity dispersion. If taken at face value and combined with an assumed distance, the implication was a galaxy with little dark matter. But the distances were not trivial to pin down, and small changes in the assumed distance altered the inferred physical quantities. The community's back and forth over DF2 and DF4 highlighted a broader lesson. Extraordinary claims, galaxies that violate the canonical idea that dark matter dominates the mass budget, require the most rigorous crosschecks across distance indicators, kinematic tracers, and environmental context. On the topic of rings and collisional systems, the observational toolkit extends to integral field spectroscopy, IFU. An IFU gives a spectrum at every pixel, so you can make two-dimensional maps of stellar and gas velocities, gas excitation states, which indicate whether the gas is being ionized by young stars or by shocks or by an active nucleus, and chemical abundances. IFU maps are ideal for distinguishing a ripple-driven ring from a resonance ring. A collisional ring shows coherent outward expanding motions and often strong star formation traces along the ring, while a resonance ring tends to be kinematically more connected to the disk and tied to the bar pattern. Mapping the ages of the stars across the ring via spectral diagnostics also tells you the timing. A very young ring suggests a recent hit, while an older ring may hint at a process that happened longer ago or an internally driven resonance. Odd radio circles ORCES are a very current example of where rapid multi-wavelength follow-up is illuminating possible origins. The radiomorphology alone, a near-perfect faint circular ring, is not enough to decide whether we're looking at a spherical shockwave, a shell from a past active galactic nucleus outburst, or some other phenomenon. Polarization measurements and radio spectral indices, how brightness changes with frequency, give clues about whether the emission is synchrotron radiation from relativistic electrons, as you'd expect in a shock or jet, or something else. X-ray and optical follow-up can search for hot gas or a faint galaxy at the center that could have produced the event. In a few cases, astronomers have found plausible host galaxies near the centers of ORCES, which leans toward scenarios involving central engines. In others, no obvious hosts appear, keeping the mystery alive. The lesson is that new phenomena often require an all-hands-on-deck strategy across the electromagnetic spectrum. When it comes to the most distant, apparently massive galaxies, the early bloomers that telescopes like Hubble and now JWST have revealed, several lines of evidence are brought to bear. Spectroscopy with infrared instruments helps break degeneracies between dusty, moderate mass systems and genuinely massive, old stellar populations. ALMA observations of dust and molecular gas can show whether a bright infrared source is dominated by dust-enshrouded star formation. If a candidate early massive galaxy shows strong dust emission, that tells you it has already been through substantial star-forming activity and metal enrichment, which is itself a clue to how quickly it assembled. Models must then account for how gas cooled and formed stars rapidly enough to produce the observed mass and metals. The direct collapse black hole scenario, positing that some black holes started with a very large seed mass formed by the rapid collapse of pristine gas under special conditions, is one hypothesis to explain billion solar mass black holes seen early on. Testing that idea requires a combination of observations: the host galaxy's properties, the presence or absence of surrounding star formation, and signatures of intense radiation or outflows from a nascent black hole. Simulations are the laboratory for probing these processes, albeit a laboratory with its own uncertainties. Large cosmological hydrodynamic simulations like Illustris, Eagle, Fire, and TNG model galaxy formation with different subgrid recipes for feedback, star formation efficiency, and black hole growth. They predict the distribution of galaxy properties, sizes, masses, colors, morphologies, that can be compared to observations. When simulations fail to reproduce an observed population of odd galaxies, theorists dig into which assumptions matter. Did the simulation allow for strong enough bursts of star formation? Was black hole feedback too weak or too efficient? Did the treatment of gas cooling and metal line cooling alter the pace of early assembly? These are the knobs that get adjusted and then tested against data. Zoom-in simulations, which focus on an individual galaxy at much higher resolution, are especially useful because they can capture small-scale physics more accurately. They help explore whether rare objects in the universe might naturally arise under particular conditions. One of the most striking areas where simulations and observations interact is in the investigation of dark matter's nature. Different dark matter models make different predictions for small-scale structure. Cold dark matter predicts many small subhalos and steep inner density cusps, while warm dark matter suppresses the formation of the tiniest halos, and self-interacting dark matter can soften inner density profiles. Observational probes include counting the number and distribution of dwarf satellites, measuring inner density profiles via stellar kinematics in dwarfs, and looking for perturbations in cold stellar streams, long, thin stellar remnants of disrupted clusters or dwarfs. A small dark subhalo passing through a stellar stream leaves gaps and wobbles. Precision astrometry, like that from Gaia, combined with deep imaging can reveal such disturbances. Measuring these fingerprints constrains dark matter's microphysics in ways that complement particle physics experiments on Earth. Another line of attack uses gravitational lensing at high resolution. Strong lensing by massive galaxies can produce multiple images and arcs of background sources. Small anomalies in these images, tiny shifts in brightness or position, can betray the presence of invisible substructure. This is a sensitive probe of dark clumps, including those that might host no stars at all. Techniques using ALMA's high resolution and sensitivity to lensed submillimeter sources have started to put strong constraints on the abundance of small mass subhalos, and those constraints feed back into which dark matter models remain viable. Turning to the Milky Way, Gaia has opened an era of galactic archaeology by providing precise positions, distances, and motions for more than 1 billion stars. That wealth of data has revealed past mergers that deposited large, coherent populations of stars with shared motions and chemical signatures. These stellar fossils tell us when the Milky Way had major interactions and how much stellar mass those events contributed. Streams traced by Gaia and follow-up spectroscopy show the shredded remains of dwarfs and globulars, and analyzing the orbits and chemistry of their stars reveals whether the progenitors were gas-rich dwarfs or more compact, metal-poor systems. This local evidence is the detailed microhistory of galaxy assembly that complements the statistical, big-picture view from high-redshift surveys. Instruments themselves have undergone a shift. We no longer just chase the brightest sources. There has been a concerted push to optimize instruments and observing strategies for low-surface brightness science. The Dragonfly telephoto array, for instance, uses dozens of telephoto lenses with special antireflection coatings to minimize scattered light and reveal extremely faint structures around galaxies. Dedicated pipelines that model and subtract the sky background very precisely allow the detection of faint shells and streams with surface brightnesses that would have been lost a decade ago. On the radio side, arrays like ASKAP and Meerkat, and later SKA, use wide fields and large collecting area to map diffuse neutral hydrogen across large volumes, unveiling extended gaseous reservoirs and connections between galaxies. Time domain surveys add another dimension. The Rubin Observatory's Legacy Survey of Space and Time, LSSD, will repeatedly image the sky deeply, enabling the detection of transient events in galaxies, flares from tidal disruption events when a star is shredded by a black hole, changes in active nuclei, or the emergence and fading of luminous supernovae that can blow bubbles and shells. Time-varying phenomena can reveal feedback in action and sometimes show effects that static imaging misses. Consider Hani's Vorwerp. It's essentially a light echo, an animated record of a quasar's past activity. Time-domain observations can catch other echoes and fading events that tell us how active galactic nuclei turn on and off over timescales accessible to human observation. Data science and machine learning are increasingly woven into the discovery pipeline. With millions of galaxies in modern surveys, automated algorithms flag candidates that look unusual in color, shape, spectral features, or variability. Machine learning classifiers can sift the bulk of routine objects and surface anomalies for human inspection. But algorithms need training sets, and that's where citizen science still shines. Volunteers have a knack for spotting genuinely strange objects that don't fit pre-coded criteria, and crowdsourced classifications have led to discoveries that algorithms might have missed or mischaracterized. The hybrid approach, machine preselection plus human vetting, is likely to remain productive as dataset volumes grow. Understanding weird galaxies also requires careful attention to biases. Surveys that are flux-limited will overrepresent bright and compact objects, while missing diffuse, faint systems. Spectroscopic follow-up tends to favor objects with emission lines because they give easy redshifts, biasing samples toward star-forming galaxies. Correcting for these selection effects is part of turning intriguing case studies into robust population statistics. Only with well-understood selection functions can astronomers say how common a phenomenon really is. Are orcs a rare curiosity or the most visible instances of a far more abundant class of events? Are the bright early galaxies exceptional or the visible tail of a broader, massive early population? There are also technical hurdles that sound mundane but matter a lot. Subtracting sky emission lines in the near-infrared, the glow of the Earth's atmosphere, is notoriously tricky and can swamp the faint signature of a distant galaxy. Radio observations must contend with human-made radio frequency interference. Deep optical imaging must mitigate scattered light from bright stars in the field that can masquerade as halos or streams. Teams developing pipelines for low-surface brightness science spend enormous effort characterizing and removing these confounders, so the faint cosmic signal emerges robustly. Looking ahead, a handful of coordinated strategies will be especially powerful for settling outstanding mysteries. One is systematic, multi-wavelength follow-up of oddball candidates. Once a radio, optical, or infrared survey flags something unusual, A coordinated campaign across ALMA, JWST, large optical spectrographs, X-ray observatories, and large radio arrays can paint a complete energetic, chemical, and dynamical portrait. A second strategy is building large, well-characterized samples rather than relying on single spectacular cases. Statistics let you test whether a phenomenon reflects a rare fluke, an environmental outcome, or a missing piece of physics. A third strategy is pushing simulations to the same observational limits. Mock surveys produced from simulations, including the same selection biases and noise properties as real surveys, let theorists compare apples to apples. If simulations fail to reproduce real samples under realistic observing conditions, that's a strong signal something in the physics or in the modeling needs rethinking. It's also worth emphasizing a practical point. Surprises are often instrument-driven. Many of the most puzzling discoveries came after new modes of observation became available: radio surveys with wide area sensitivity, deep optical imaging that preserves low surface brightness, or the infrared reach of JWST. That means the next round of surprises likely lives in data we haven't yet gathered with the same depth or fidelity. The SCA, Rubin Observatory, Roman Space Telescope, future X-ray missions, and next-generation gravitational wave observatories will open new parameter spaces. And wherever a new window opens, the universe tends to show us phenomena we hadn't imagined. All of which leaves us with a guiding principle. Whenever you see an oddball galaxy, think multi-probe. Ask, what does its light tell you about its stars? What do its emission lines tell you about gas, metals, and ionizing sources? What do motions tell you about mass? What does its environment say about past interactions? What does it look like in radio, millimeter, infrared, optical, and X-ray? By layering those answers, astronomers can reduce ambiguity and construct plausible life histories for even the most puzzling systems. From the practical side of designing observing programs, astronomers increasingly favor targeted breadth. That means instead of taking many deep spectra of similar objects, teams will sometimes take shallower, diverse datasets across many wavelengths for a smaller selection of the most puzzling objects. A modest optical spectrum, an ALMA pointing, a radio continuum map, and an X-ray exposure together can often answer more targeted questions than a single very deep observation in one band. The trade-off depends on the question. If you need a definitive distance, you need a deep optical or infrared spectrum. If you need the mass of cold gas, ALMA or deep co-observations matter. A prioritization that combines urgency, how likely is the target to change our thinking, with feasibility, can a given instrument realistically get the needed data, tends to steer follow-up decisions. Another operational trend is rapid response. Transient behavior, a flaring nucleus, a sudden jet outburst, or changing-look quasars can give unique windows into cause and effect. Facilities that can quickly repoint to capture an event in multiple bands are invaluable. Time domain surveys that flag variability and multi-wavelength networks that can respond in hours to days are therefore more vital than ever. Finally, as data volumes explode, so does the need for robust archiving and interoperability. A radio detection cataloged in Perth may hold the key to an optical oddity studied in Chile, and only by sharing data and metadata can these connections be spotted. Projects that make their data publicly accessible and well-documented enable the broad community, including citizen scientists and cross-disciplinary researchers, to spot correlations and new classes of objects that one team might miss. So we keep a mixed strategy: wide surveys to find the weird, targeted follow-up to characterize it, sophisticated simulations to understand which physics could produce it, and coordinated, rapid response observing to catch the transient pieces of the story. That is how the scientific method presses at the edges of our understanding, by finding anomalies, laying down rigorous tests, and updating models to match the measurements. And as the instruments and methods continue to improve, the kinds of mysteries we can address will only expand. We've talked about how astronomers find odd galaxies. what instruments and simulations bring to the table, and why anomalies matter. Let's look now at how those threads weave together in real-world programs, and what we can realistically expect in the next decade. Not as a dry forecast, but as a sense of how the hunt for cosmic oddballs is going to change the questions we ask, and the kinds of answers we might get. First, the observational landscape is about to become dramatically richer and more varied. The Rubin Observatory will amount to a time-lapse movie of the visible sky. It will revisit the entire southern sky every few nights for 10 years. That will do two big things for weird galaxies. One, it will catch transients and variability in galactic nuclei and starbursts on human-accessible timescales, giving us a chance to observe flaring events, jets turning on or off, and exotic transients that could leave long-lived marks on a galaxy's appearance. Two, by coding hundreds or thousands of exposures, Rubin will push the limits on low-surface brightness imaging across huge swaths of sky, revealing faint tidal streams, shells, and diffuse galaxies that are currently invisible. That combination, time domain information plus unprecedented faint structure sensitivity, will let astronomers distinguish events that are fleeting from features that are long-lived, and it will build large, statistically useful samples of objects that used to be one-off curiosities. In radio astronomy, the SKA and its precursors, MeerKAT, ASKAP, and others, will produce HI maps orders of magnitude deeper and wider than today's best surveys. Neutral hydrogen is the raw fuel for star formation, and often the most extended baryonic component of galaxies, so mapping its distribution on large scales is fundamental. If there are genuine dark halos with gas but no stars, SKA-like surveys would find them. Rotating HI clouds in otherwise empty space would be a smoking gun. But even if those objects remain elusive, the surveys will map the filaments, bridges, and tidal streams of gas that fuel galaxies, and show us, in population terms, how common various gas configurations are. Large radio surveys will also uncover more ORCES and other diffuse radio phenomena, and because these telescopes are designed to cover wide fields, they will give the environmental context that's so important when deciding between explanations like central AGN outbursts or expanding shock shells. The infrared and submillimeter regime will continue to be transformed by JWST and by ALMA-like facilities. JWST's infrared sensitivity lets us push into dusty, redshifted parts of the universe where starlight has been shifted into longer wavelengths. That capability is already reshaping our view of the earliest galaxies, and as more fields are observed and deeper spectra are obtained, we'll either confirm that the early universe had more massive systems than expected or reconcile the apparent tension by refining mass, age, and dust estimates. ALMA and the next generation of M/SUB-instruments will continue to map cold molecular gas, the immediate star-forming material, down to small physical scales in both nearby and distant galaxies, revealing whether extreme starbursts are compact nuclear beasts or more distributed phenomena, and how gas is funneled into the centers to feed black holes. On the simulation side, there's a parallel revolution. Computational power keeps growing, and more importantly, simulation teams are getting better at including realistic physics while producing larger statistical samples. Instead of simulating a single galaxy at extremely high resolution, many groups now run large cosmological boxes with enough resolution to form thousands of galaxies, and to include physically motivated recipes for star formation, feedback, and black hole growth. Some projects are also coupling cosmological simulations with radiative transfer codes that predict what those simulated galaxies would look like to real telescopes, including realistic observational effects like noise, point spread functions, and surface brightness thresholds. That means modelers are not just predicting intrinsic properties. They can produce mock surveys that mimic the observational biases and selection functions of instruments like Rubin, JWST, and SKA. When simulations and observations are compared on an even playing field, the mismatches that remain are far more informative. A concrete example of this approach is how theorists are tackling ultra-diffuse galaxies. Instead of arguing in generalities, they generate mock images of simulated galaxy populations and ask which of their simulated objects would be identified as UDGs in a realistic survey. They then check whether those simulated UDGs formed by puffing up from strong internal feedback, by tidal heating in clusters, or as failed massive systems. The results suggest multiple formation channels are likely in nature, with the balance depending on environment. Observational campaigns then test those predictions by measuring globular cluster counts, internal kinematics, and stellar populations. That iterative back-and-forth, simulation predicts, observers test, modelers revise, is exactly how the field will converge on robust stories for the odd systems. One area where the interplay of instruments and modeling will be decisive is in the study of the circumgalactic medium, CGM. The CGM is the tenuous halo of gas surrounding galaxies out to hundreds of thousands of light years, and it acts as both reservoir and waste bin. Gas flows in, cools, and forms stars. Stars and black holes inject energy and metals back into it. Observationally, the CGM is difficult because it's diffuse, but new techniques are revealing it in unprecedented detail. Absorption line studies using bright background quasars and galaxies already show that halos are clumpy, filamentary, and chemically enriched. Direct imaging of CGM emission is becoming feasible with sensitive integral field units and with stacking techniques, revealing extended ionized gas and subtle kinematic patterns. Simulations predict that the CGMS structure is sensitive to feedback strength, mass, and environment. So mapping the CGM across galaxy types and epochs will strongly constrain the subgrid physics used in galaxy formation models. That in turn tightens the predictions for how often dark or extremely faint galaxies should occur. There's also a growing appreciation for multi-messenger constraints. For example, direct detection experiments and collider searches for dark matter particles inform what kinds of dark matter are plausible. Those particle physics constraints, folded into cosmological simulations, change expectations for the number and structure of small halos, and thus for the existence of dark galaxies or the internal dynamics of dwarfs. On the gravitational wave side, future space-based detectors like LISA will detect mergers of supermassive black holes, providing an independent line of evidence for the rate of heavy galaxy mergers over cosmic time. Combining gravitational wave event rates with electromagnetic surveys of merging galaxies will provide an unprecedented, cross-validated picture of how galaxies and black holes pair and coalesce. Machine learning will continue to be a prominent tool for finding weirdness rapidly in enormous datasets. The simplest use is classification. Teach an algorithm what a normal, spiral, or elliptical looks like, and then flag outliers that deviate strongly. More advanced techniques use unsupervised learning to find clusters in high-dimensional parameter space, colors, shapes, spectral features. The regions where normal objects dominate will be obvious, and the fringes reveal candidates for new classes. But caution is warranted. Algorithms reflect their training data and can be fooled by instrumental artifacts. That's why the human element remains important. Citizen scientists often catch genuinely interesting oddities that automated pipelines miss because humans are good at pattern recognition in noisy, complex contexts. The combination, automated preselection with crowd or expert vetting, is proving powerful and will scale well in the era of Rubin and SCA. Technical challenges will remain and will require ingenuity. For low-surface brightness science, control of scattered light and precise background subtraction are crucial. Small errors can create or erase diffuse features. Radio arrays must contend with radio frequency interference, RFI, from human technologies, which becomes harder as we build more sensitive instruments. The infrared regime must wrestle with thermal emission from the telescope and the Earth's atmosphere. Overcoming these obstacles is partly a hardware problem, better shields, optics, and site selection, and partly a software problem. Smarter pipelines, more sophisticated statistical models for the background, and the systematic archiving of metadata so subtle instrumental effects can be traced and corrected. One area where surprises are particularly likely is in the time domain. Consider active galactic nuclei, AGN. We used to think of AGN as relatively steady on human timescales, with variations on months to years at most. But surveys have revealed changing look, AGN, that can dramatically change their spectral signatures and brightness on timescales of years or less. It turns out quasar engines are more variable and responsive than once thought, and events like sudden accretion episodes, disk instabilities, or minor mergers can trigger rapid changes. When an AGN flicks off after illuminating a gas cloud, that cloud becomes a light echo whose morphology and ionization state carry a record of the AGN's past. Hani's Vorwerp was a classic example. Time-resolved surveys will likely find more of these echoes, giving us a way to study the duty cycle of black hole feeding in many galaxies, and to connect short-term AGN variability with long-term galactic consequences. Another promising angle is the use of stellar streams as probes of invisible structure. These thin, coherent trails of stars formed when a small galaxy or globular cluster is shredded by tidal forces are exquisitely sensitive to perturbations. If a dark, starless subhalo passes through a stream, it will leave a kink or a gap. As Gaia and deep imaging map more streams in the Milky Way and in nearby galaxies, we're essentially setting up a network of detectors for dark lumps. The statistical properties of stream perturbations will constrain the abundance of low-mass halos and therefore the nature of dark matter. Theoretical work has already shown that different dark matter models leave different signatures in stream populations, and the coming observational datasets will put this to the test. When anomalies persist, they tend to motivate creative physics, sometimes modest, sometimes radical. For instance, the cusp core problem in dwarf galaxies, whether inner dark matter density profiles are steep cusps or shallow cores, has driven investigations into baryonic processes that can redistribute dark matter via energy injection from supernova-driven gas motions. Alternatively, it has motivated particle physics proposals like self-interacting dark matter, which naturally produces cores. Both routes are scientifically healthy. One explores whether complex baryonic physics suffices, the other asks whether new particle physics is needed. The same debate applies to other tensions. Rather than jumping to new physics immediately, the community tries to exhaust astrophysical explanations first, and that process itself often yields new insights into how galaxies behave. Let's bring this down to a few specific case studies to make things concrete. Suppose a new radio survey detects a large, circular HI structure with no obvious optical counterpart. The initial excitement will mirror the early dark galaxy hype. Is this a gas-rich, star-poor halo, a dark galaxy, or is it tidal debris? The follow-up playbook is familiar. Get deep optical and infrared imaging to search for faint stars. Obtain spectroscopy of any faint stellar candidates or of the gas itself to measure metallicity. Map the HI at higher angular resolution to look for ordered rotation. Survey the surrounding region to identify plausible interacting galaxies, and run kinematic models to see if the velocity pattern is consistent with a bound, rotating disk or with an expanding tidal loop. If the structure shows low metallicity, coherent rotation over large radii, and isolation from plausible donors, the dark halo hypothesis gains real weight. If instead the gas is metal-rich and connected to a nearby disturbed galaxy via a faint bridge, the tidal origin is likely. Either way, the process yields a richer environmental and physical story than the initial detection alone. Another imagined case. Rubin finds a population of previously unnoticed, faint, blue compact blobs that brighten and fade over months, clustered around the outskirts of star-forming galaxies. These could be supernova-powered knots, temporary starburst regions triggered by recent gas inflow, or the visible manifestations of shocked gas illuminated by passing AGN jets. Rapid multi-wavelength follow-up, optical spectra to identify supernova features, radio and X-ray to search for jets or shocks, and ultraviolet imaging to trace hot young stars, will discriminate among possibilities. Even if each blob is transient, their statistical properties, how often they appear, where they're located relative to galactic centers, and their spectral signatures, will teach us about the prevalence of short-lived star formation episodes and about how gas is compressed on small scales. Consider as well the early massive galaxy problem. Suppose JWST confirms a handful of galaxies at Z10 with stellar masses that challenge current simulations. Those objects will become targets for intense scrutiny. ALMA will seek dust and molecular gas. Spectra will search for metal lines to assess chemical enrichment. Gravitational lensing models will be examined to check for magnification biases. And theorists will run targeted zoom-in simulations to explore whether rare density peaks or unusual star formation efficiencies could produce such systems naturally. If the population persists and statistics grow, theoretical models will either have to accept a broader parameter space for early star formation, for example, top-heavy initial mass functions or episodic, highly efficient bursts, or consider alternative pathways like early, massive black hole seeds that alter the baryonic assembly of their hosts. Either route would feed back onto our understanding of the epoch of reionization and the early thermal history of the universe. There's also an educational and citizen science angle worth noting. Many striking discoveries, Hanny's Vorwerp, green peas, and several peculiar morphologies, came from volunteers inspecting survey images. As data volumes balloon, the role of citizen scientists will shift. Rather than being the primary screeners for millions of images, volunteers will become specialized discovery partners. They'll be trained to look for specific kinds of anomalies, help curate training sets for machine learning, and participate in follow-up investigations that require careful visual assessment. That human-machine partnership will probably be one of the most efficient ways to keep serendipity alive in an era of automated pipelines. Now a practical word on scientific culture. When something strange appears, the proper scientific reflex is cautious curiosity, not instant sensationalism. The history of candidates that turned out to be artifacts, misinterpreted distances, or tidal imposters teaches humility. That's not to dampen excitement. The real thrills come with careful, often tedious confirmation work. The community has developed healthy norms. Extraordinary claims require multiple, independent lines of evidence. Data and analysis code are expected to be shared publicly so others can reproduce the result. And follow-up resources are allocated based on a combination of plausibility, potential impact, and feasibility. Those norms are why the weirdest objects often take years to fully understand, and why the ultimate payoff, a robust new piece of physics or a revised formation pathway, is worth the wait. What would a decisive discovery look like in this field? There are a few possibilities that would be paradigm-shifting. A population of isolated, rotating HI clouds with little to no stellar content, clearly embedded in massive dark halos, would provide direct evidence for dark galaxies and reshape how we count baryons and dark matter on small scales. A statistically significant population of early, massive galaxies that cannot be reconciled with any plausible baryonic physics would force a rethinking of early structure formation, perhaps pointing to new modes of star formation, unusual initial mass functions, or surprises in dark matter behavior. The robust detection of many self-interacting dark matter signatures in dwarf galaxies or stellar streams would change our notion of dark matter from a passive gravitational background to a particle species with non-trivial collisional physics. Any of these outcomes would be major breakthroughs, and they are exactly the kinds of discoveries that keep instrument teams, observers, and theorists working together. Finally, what do these efforts buy us intellectually? Odd galaxies are not a niche hobby for specialists. They are stress tests for the broader narrative of how the universe made structure. They help answer questions like, how and when did baryons and dark matter decouple in the assembly of structure? How efficient is star formation in different environments and epochs? How do black holes and stars influence each other's growth? How does the local cosmic environment channel or interrupt galaxy evolution? The beauty of focusing on oddballs is that they often magnify the leverage we have on these questions. A galaxy that violates a key expectation is a spotlight on the missing physics. In practical terms, studying these systems sharpens the predictive power of simulations that feed into many areas of astrophysics, from interpreting cosmic microwave background foregrounds to understanding the conditions for planet and life formation in different galactic neighborhoods. The same physics that governs gas inflows and outflows in a strange ring galaxy, turbulence, cooling, feedback, also shapes the molecular clouds where stars and planets form. So the ripple effects of studying cosmic oddities extend across scales. We began by noting that galaxies are not tidy islands, but messy, dynamic systems with histories written in stars, gas, and motion. The most mysterious galaxies are the ones that force us to read those histories more carefully. With new telescopes, smarter simulations, and an evolving human-machine discovery ecosystem, the coming decade promises not only more oddballs but better ways to interpret them. Those interpretations will refine our understanding of dark matter, star formation, black hole growth, and the role of environment in shaping cosmic evolution. And when an especially stubborn mystery finally gives up its secrets, the payoff will be more than a resolved anomaly. It will be a deeper, more accurate story of how the cosmos built the galaxies we see today. So keep watching the skies. The next weird galaxy is already out there, and the tools we're building make it likelier than ever that we'll not only spot it but make sense of it.